Okay, so today it's sound and light, and that really means wave motions. I'm afraid it's all getting a little bit more sort of physicsy and gosh, equations and things, but let's hope you can sort of bear with it. So, sound and light, wave motion. I don't know whether any of you have ever been stuck in a traffic jam on a motorway and you're completely stationary, and then the cars in front of you start moving and you think, oh, goody, goody, so you accelerate. And sometimes you can get up to quite a reasonable speed and you think, oh, it's all cleared. Oh, no, it hasn't. No, there are all lights coming on at the front. Oh, dear, and you slow down and down and down until you eventually stop. And you sit for another 4 or 5 minutes, and then, oh, we're starting to go again. And you are participating in the sort of wave motion at this point. If you could hover above the motorway and look down, you'd see, as well as everything inching forward, decompression waves sort of rolling backwards down through the queue of traffic. Because if your acceleration is affected by the distance between you and the car in front, or more particularly, perhaps the difference in distance between you and the one in front and you and the one in behind. So in other words, if the front distance is increasing, you accelerate. And that is the sort of condition that makes wave motion. And that essentially is what sound is. Now I'm going to share a screen and show you this, I hope, which shows what sound looks like, which is a longitudinal wave. Now you can see that little red thing in the middle. That is a particle of air, and that isn't actually moving forward. It's just diddling backwards and forwards, if you can see it. Now, I hope people on the phone can see it, but there's a little red spot in the middle, which is just going backwards and forwards like that. And all of them are doing that. And that is what's creating this rippling of regions of high pressure where the dots are closer together and regions of low pressure. And that's what a sound wave looks like. It's believed that Leonardo da Vinci was the first who thought that sound might be something like that. And Galileo followed on by associating the frequency with the wave with the pitch of the sound. I'll come on to that in a moment. Good old Boyle, you may remember of gas law fame, showed that it was something to do with air because he got a bell going inside a vacuum flask and sucked all the air out, and then you couldn't hear the bell going. And when you let the air back in, you could. So he thought, aha, yes, well, sound is carried by air then. So that is what sound is, and there are a few little points to make about waves. First of all, there's a sort of, and all of these I'm afraid crop up later broadly, so it's worth, there's nobody joined yet. So very crudely, sort of, I'm going to talk about the displacement d, which is the distance that that little red blob had moved away from its equilibrium position. And really I'm saying that if the change in d with time, broadly, I mean it's actually double change in time, but we'll leave that, is equal to some sort of constant times how this displacement changes with distance. Sorry, I might not be able to see that awful writing. That is what gives a wave when the rate at which the thing accelerates in time depends on how the spacing in the distance is changing. And there are two features that define a wave, really. The number of peaks going past any point in a second, which is the frequency, or f, and the distance between the peaks, which is known as the wavelength, which is given the Greek letter lambda. And since that's the number of peaks that go past in a second, and that's the distance between peaks, the product of the two is the length of wave that goes past a point in the second. So that is the speed of the wave. And because for something like sound in air, say, the speed of the wave is constant, if you have a high frequency, you've got a short wavelength. So if that number's big, then this one has to be small. And if that number's small, then this one has to be big in order that the speed is the speed of sound in air. So as an example, middle C on the piano is about 260 cycles per second, which has a physics unit of hertz, because Mr. Hertz did something with sound. I can't actually remember what, but anyway, so middle C is 260 hertz. The C above would be double that. Going up by an octave doubles the frequency. So the note C above middle C is 520 odd hertz. The next one up is 1000 hertz. And the wavelength of this is, well, going back to good old imperial units, which looking at the people here is probably all familiar to, is about 4 foot. So it's about 4 foot wavelength for middle C. The C below middle C has an 8 foot wavelength, and the C below that, bottom C on the cello, has a 16 foot wavelength. The next thing to remember about waves is that if they're confined in something like a tube or a box, the only wave that can reasonably survive is the one that sort of, if you like, fits in, or ones that fit in. So if you've got an organ pipe, say, the waves that are created by the pressure of air being blown into it rattle up and down inside, and the wave that goes from here to there and then bounces back, and by the time it comes back here again, has done one complete wavelength, say 4 foot's worth, is the wave that you get out of a box like this. And so all musical instruments, all sort of proper musical instruments, not electric ones, work on this sort of principle. All wind instruments work on the fact that if you have the right length of tube, that defines the wavelength and hence the pitch of the note that you get out. And hence you may have noticed on organs, they describe the stops in terms of 8 foot and 4 foot and things, which tells you whether it's basically the notes are going to be low if it's a 16 foot stop, or very high if it's a 2 foot stop. And guitars and things all work by trapping a wave on a wire. Can you see that? Yes, between 2 fixed points at the end. And again, if you get a complete wave going from here to there to back again, that has to have a wavelength equal to twice this distance. And so the distance, again, determines the wavelength of the wave and hence the frequency of the note coming out. So that's something which will crop up later on. So it's just useful to have this idea that when a wave is confined in a box, there are only particular frequencies that work. I mean, you could have, that would also work. You could have something which does a whole wavelength there and then a whole wavelength back. That would also fit, and that would be twice the frequency. But it has to be something that fits in neatly. So that's one thing about waves. Another thing about waves is that they can easily go over the top of each other. Now, if you're listening to an orchestra and there are trombones blasting away and cellos sawing away in front of them and violins on this side and horns at the back, if you like, the sound from the trombone doesn't sort of bounce off the sound from the cellos and it all get mangled up and ruined. They can all go over the top of each other and you just hear trombones and cellos and horns and violins all at once, because all the sound waves are coming at you and they can ride over the top of each other very easily. The note so called the principle of superposition. And one way in which this is sort of utilized these days, and I'm going to draw a wave now as a sort of graph, if you like, that supposing this is a wave that we've got coming out of somewhere, and this might represent pressure, for instance, if it's a sound wave and this is time. Supposing you've got a wave like that being generated from somewhere, if you manage to generate another wave which is going exactly opposite to it, the two will add up to give you pretty much nothing. And that's basically what so-called noise-cancelling headphones do. They presume have a little microphone on the outside of the headphone, which receives the sound that's coming at you from the outside world, and then a bit of electronics inside generates, as best it can, a completely inverted signal, which it sends to your ears to sort of cancel out the sound that's creeping in through the headphone structure. So that's quite a useful characteristic of waves, as I say, that they sit on top of each other and that you can sort of, if you're clever, you can cancel out one by sending its inverse on top of it. Now then, this turns out to be a useful little part of our exploration of how, what share screen, where are you? Yes, we'll go back to that. I hope you can see that now. And let's go on to the next thing, which is this. Now that's showing what happens if you have two sources near to each other, both emitting waves. And now then, I'm sorry that I'm a bit ponderous with the annotate thing, spotlight. Now, yes, there we are. So you can see that along this line here, which is the dead center, the waves coming out of this one are going to curses. The waves traveling out of the left-hand little output and the ones coming from this side are going to travel the same distance each to get to this point here, in fact, to get to anywhere on that line. So they add up together and you get a visible wave. However, on somewhere like here, the wave coming from the left-hand one of the two has gone a slightly shorter distance than the wave coming from the right-hand one. And if that distance is half a wavelength, the two waves are pretty much opposite to each other, so they add up to give pretty much nothing. And all the way along here, that is true. So you get a sort of band of nothing much, and then you get a band of quite a lot. And then on the other side, again, now the right-hand one's got to travel slightly less far than the left-hand one. So you find a sort of pattern of bands of brightness or loudness and then bands of softness. And if you walked past two loudspeakers doing that, as we used to do at the Sixth Form College, you'd hear it being loud and soft and loud and soft and loud and soft as you walk along this direction. So that's a useful little scheme for determining whether something is fundamentally a wave motion or not. And that is what our friend, I think that might have turned you off. No, it hasn't. Thomas Young, this is where he comes into the frame. And you'll notice that all the people we've got here are now getting into the sort of late 1700s, 1800s. So we're creeping on through timelines to, in our little physics exploration. So Thomas Young basically did an experiment like that with light. And so what he did was, I mean, it was actually a bit similar to this, but not exactly the same, but the sort of version of his experiment that's now universally done, and which we did again with students at the sixth form college to show that light is a wave, basically involved having two little slits illuminated by something. In Young's case, it was probably the sun, but now you can use a strong light. And these are need to be very close together. So, you know, about 1 millimeter. What we used to use was a slide, black slide, with two very, very thin lines drawn down it, 1 millimeter apart. And then you observe what sort of pattern you get shone on a screen. Now, the trouble is the pattern, I'll just go back to that, to the share screen thing. Come on, where are you going to do the share screen thing? Yes, I'm going back to that. This pattern, you can see that in this particular case, the two sources are separated by something which is obviously about the same as the wavelength, which is, you can see the distance between the peaks. So if the sources are only a few wavelengths apart, these bands of brightness and darkness are going to be quite spread out. But because it turned out that light has an extremely small wavelength, you actually, the angle between the region of adding up and the region of counteracting each other is very, very, very small. And the only way you can really see anything is to have the screen about 6 feet away from the two slits, which of course means that the light that gets there, as there are only two miserable little slits, is very dim. So you have to have all the blinds down and the light that's shining here very well shrouded. So there's just the light from these two pathetic little slits, and then about 6 feet away, 2 meters away, if you're lucky and you're dodging around amongst the students to see if they've got it set up right, you might be able to see a little sort of pattern of darkness going light and then darkness. So this is what you get, a little pattern of thing, and then it all sort of fades away. But this was referred to as fringes because they look a little bit like sort of tassels hanging on the bottom of a curtain. And by measuring how far apart they are, and knowing the distance from the slits to the screen, and knowing what this separation is, you can work out what the wavelength of light is, and also by observing this at all, demonstrate that light is indeed a wave. And that's what old Young did. And Young's slits is the classic demonstration of the wave nature of light. Because before that, Newton, for instance, thought it was a stream of little particles, or little corpuscles, as he called them. This was the first demonstration that no, light was actually some sort of a wave. And it has a very small wavelength, less than 1/1,000,000th of a meter, less than 1,000th of a centimeter. So it's tiny. This is why the sort of effects are very difficult to spot. So that was Young's discovery. But of course, it begs the question then, well, it's a wave of what? In what? Because it travels across space where there isn't anything. So what is it? What's it a wave of? Well, mystery. So we'll need to park that for a moment and then go on to consider some other things that were being investigated at the time, which is by these bodies. So we've done Thomas Young. Now we have Monsieur Coulomb and Signor Volta and Michael Faraday and James Maxwell. So these are the sort of players in the world of electricity and magnetism, which was something else which was beginning to puzzle people. And you can see now we're definitely into the sort of late 17s, early 80s. This is where people were getting into sort of experiments and so on, and wondering, what is this strange phenomenon that when you rub two different materials together, sometimes you end up getting sparks and they attract each other, and you can pick up bits of paper if you've charged up a sort of amber rod on your sleeve and then hold it over little bits of paper, they sort of jump up to it. What on earth's going on with that? Very interesting. Well, dear old Monsieur Coulomb did quite a lot of work on this. I'm afraid I don't really know the details, but it became apparent that there was a mysterious property of materials known as charge. Now, what it was, who knows? It seems to be sort of something that things have, rather like mass. There's a positive type of charge and a negative type of charge, and it seems that if you rub two materials together, you sometimes manage to sort of pull some of the negative charges off one of them and leave the positives behind, perhaps. You can sort of charge things up like that. And dear old Coulomb worked out, now you may remember, says he, more equations, that Newton's law of gravitation was that there was a force between any two objects given by the product of their masses divided by the distance between them squared times this constant g, which was very, very small because gravity is so pathetically weak. Well, now Coulomb discovered by charging up pith balls and observing how strongly they repelled each other, he discovered that there's a very similar sort of force, which I'll just call it like that at the moment, where the expression for a charge is usually Q. The electric force between two things is exactly the same. The product of the charge on one thing times the charge on the other, divided by the distance between the two, times some constant or other, which effectively gives you the force between two things of unit charge, a unit distance apart. Like that gives the gravitational force between two things of unit mass, a unit distance apart. And whereas this was 0 point and then about 11 noughts 1, this is about 10 1 followed by 10 noughts. So this is much, 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 much bigger than that. The electric force is much, much stronger than gravity. Now, of course, it obviously depends a little bit on what you choose as your units, but it is certainly the case that in the lineup of forces in nature, electricity thrashes gravity. The electric force is a much stronger force of nature. So that was what Coulomb discovered, that there seems to be this property that things can have, and it obeys a sort of force law like mass does with the force of gravity. Volta, the next bloke that we saw, went further and discovered that also this mysterious charge stuff can flow. It can flow, what it is, I don't know, but it can flow in metals particularly. And you can sort of get it going with different metals stacked on top of each other. So dear old Mr. Volta, after whom of course the volt is named, invented basically the first batteries by sticking different metals together and finding that it caused charge to flow in a wire. And he also, because people were discovering that there's electricity is involved in animals. And in fact, they had thought that that was the only place you got it. But old Volta amused everybody once he got his batteries going by jamming wires into the legs of a dead frog, and they jerked, you see. And you say, ah, there we are, see, it's electric impulses. That's what gets them going. So that was another characteristic of charge, that it seemed to be able to flow in things, and that if you sort of somehow built up a pressure by fiddling around with different metals, you could get it to flow around a circuit. And then old Faraday, now I think he was really in a different league from the other two. He really did break ground. He went on, first of all, to think about magnetism. Now that's a strange phenomenon too. Oh, as we're now looking at those. Well, now magnetism is a funny thing. That is another force at a distance. And if you put a magnet under a bit of paper and then sprinkle iron filings all over the top of it, you get something that looks like that. And it sort of suggests something coming out of the magnet. It certainly suggests what became known as lines of force. And Faraday sort of developed this idea into the concept of a field, a magnetic field. He said, well, as you could say that a magnet establishes in the space round it a magnetic field such that at any point in space round it, there is a particular force that would be exerted on a unit pole. Actually, I say it's conventionally a north pole, so it would go that way. Anywhere you put it, you would find that a particular force would be exerted on a unit pole. And he conceived this idea of representing this mysterious field in space by lines of force. The closer together they are, the stronger the field. And the direction of them shows the direction in which in this case, a free north pole would move. And we do the same thing with charge. If you've got a charge Q here, plus, then represents the electric field round the thing, which shows that a positive charge would move directly away from it along these lines. Again, the closer together the lines are, the stronger the field. And in 3 dimensions, actually dead straight lines like that coming out of a central point do indeed get weaker as the square of the distance that you're going away. So it all works very nicely. And it turns out to be quite a convenient mechanism for working out what's going on. For instance, if you use old Volta's batteries to charge up 2 plates like this, so you've got a battery around here, and you've shoved on sort of positive charges on this side and negative charges here, the electric field between the two, you could more or less, by just thinking, well, it can't really wobble about all over the place, because why should one bit be any different from another bit? Presumably, it really can only be nicely uniform like that. And, it presumably does something a bit odd at the edges. It starts getting a bit flaky out here, probably. But in the middle, there's really nothing it can be except nice straight lines like that, equally spaced. So you can sort of, rather than try to work out, so if you have a little charge here, rather than try to say, well, what's the force on it from this one and that one and that one, you know, and what's the attractive force from all of these up here, and you'd be an absolute nightmare. You can just say, well, okay, the field exerts a force. Now, when we get back to these equations, so you see what I mean? It's all good equation time. What you can sort of say is that, if you like, this represents an electric field, E, which is set up by the big Q, and the little q would experience a force anywhere in space equal to the strength of the field times its charge. And you can actually do just the same with gravity and say, well, okay, that is the gravitational field, if this is the radius of the Earth, that's the gravitational field set up by the Earth at its surface. And so the force you get on that I'm going to call G is equal to G, the gravitational field times the mass. So these turn out, particularly in the case of electricity, to be a very useful way of calculating what's going on. But do they exist? Is there actually such a thing as a magnetic field and an electric field? Well, not really. I mean, there's nothing really there. It's just a sort of mathematical convenience, isn't it? Well, it is and it isn't. Very interesting. But that is certainly a challenging thought, that this is really, there aren't really lines of force, but it turns out to be a very helpful way of thinking about and calculating what's going on. Now we come then to the final piece of the equation, which is, now we go back to that again, where dear old Faraday comes in. And I think we've got him. Oh yes, no, I've skipped a bit. Another thing that Faraday discovered, or was beginning to be realized, was that there was an also interesting connection between electricity and magnetism. If you have a current, an electric current, a flow of this mysterious charge going through a wire, it makes a magnetic field round it, as you can see by the iron filings on that diagram. And Faraday further discovered that you could actually make a current flow by waving a wire around in a magnetic field. So a current, an electric current makes a magnetic field, and a magnetic field, waving around, can make a current flow. So they're all interconnected. Very interesting. And then along comes Maxwell, who, poor chap, died of cancer pretty early, as you can see. He comes from southwest Scotland, and again, now he's an even bigger physics noise than Faraday. Faraday and Maxwell between them. Apparently Einstein said, when he was being shown over some university or other, said, you know, the remark was raised that he stood on the shoulders of Newton. And he said, no, I didn't. No, I stood on the shoulders of Maxwell. That's who I stood on the shoulders of. So Maxwell was a very big noise, and intriguingly was, you know, really getting into the mathematics. And his big thing was working out a set of equations that related precisely the magnetic fields and electric fields. His equations, known as Maxwell's equations, defined exactly how a magnetic field changing creates an electric field, and how an electric field changing creates a magnetic field. And his 4 equations completely summarize the way in which electricity or electric fields and magnetic fields are related to each other. And then when he'd done them, this is slightly sort of, well, simplifying, but basically he looked at them and thought, well, that's interesting, isn't it? Because if I stick them together, I get something that looks like my sort of wave equation. I get things changing in time here, equally depending, or something changing in distance over here, influencing what's changing in time over here. Oh, it's a sort of wave equation. What on earth would a wave of electric field be, I wonder? Goodness me, or a wave of magnetic field. What on earth can that be? Well, of course, conveniently, a wave equation always includes in it something which tells you what the speed of the wave is. So, okay, in these equations that I've got with funny little constants to do with electricity and magnetism, let's see what the speed comes out as. So calculate. Oh, it comes out as the speed of light. Oh, well. Oh, so light is a wave of electric and magnetic fields. Oh, aha, I think I see a paper to the Royal Society coming on here. Yes, isn't that interesting? And he then went on to think, well, now, if that's really all it is, a wave of electric and magnetic fields, presumably the wavelength doesn't have to be this strange sort of fraction of a thousandth of a millimeter that light is. Presumably, if you got a current going backwards and forwards in a wire, that's going to cause an oscillating electric field. So presumably it ought to make waves, oughtn't it? With just much longer wavelength. I wonder if it does. Well, of course it did. Radio waves. So that led to the whole business of radio and radio waves, and was really rather a triumph. And of course, then we discovered, or it emerged, and we're now sort of skipping on, that the light is only a tiny little bit of what's known as the electromagnetic spectrum, which can have waves just like sound waves. You can have them sort of 32 feet long to, a fraction of an inch long, low notes and high notes. Light is in here at about just less than a millionth, and that's 10 to the minus 6, that's 1 over a million here. But, and this shows the wavelength in, well, really doesn't really matter, but it's a very, very short band. But below that, with longer wavelengths, you get the so-called infrared, which is a sort of heat. Then comes microwaves with longer wavelengths still. So this is now about a millimeter, that's a meter. And radio waves, well, you might remember sort of long wave radio is really great big long wavelengths of sort of hundreds of meters. On the other side, ultraviolet has even shorter wavelengths than violet, and X-rays even shorter still. And all of these are illustrated on the next slide. I'm going to be sticking with slides a bit now. So this again just illustrates the sort of things that we now use all these different parts of the electromagnetic spectrum for. Sun is vigorous in this region here, so the visible band and a bit of ultraviolet and a bit of infrared. X-rays are up here, and beyond that we get these mysterious things, gamma rays, which we might touch on later. Below, by the time you get to about a millimeter wavelength and longer, this is the region of microwaves, microwave ovens and things like that, and of course increasingly mobile phones and stuff, for a reason which I might have time to explain. Then below that there's the traditional radio frequency spectrum. It tends, whereas at this sort of region, up until sort of infrared, one tends to talk about distinguishing them by means of their wavelength. So infrared is a millionth of a meter long, or a micron. These are less than that, so hundreds of nanometers. These are only tens of nanometers. In this region, one tends to talk about the frequency. So microwaves are sort of less than 30 gigahertz. That's a billion cycles per second. Radio frequency getting into megahertz and kilohertz. You may remember that sort of expression from 98.4 megahertz or something, radio stations. And so Maxwell's sort of discovery unlocked all of this realization that our bit of light that we see is only a part of this great spread of electromagnetic waves. A couple of other, a few other little points just before I sort of conclude. Perhaps conveniently, now it turns out that hot bodies give out a particular sort of pattern of radiation, which depends on the temperature. The hotter the thing is, the shorter the wavelength that the peak radiation is. So this is the sort of shape of what they call a spectrum that the sun gives out. So in other words, most of the energy that the sun pushes out is actually in what's known as the visible band. In other words, the part of the spectrum that we can actually see with our eyes. Red is long wavelengths, blue and violet is short wavelengths. And as you can see, the sun's peak is pretty much smack in the middle of our visible band. But there's quite a bit of energy produced in the sort of high infrared along here, and a certain amount in ultraviolet too. And the hotter stars would have that peak further over towards the ultraviolet. And that was a bit of a problem because actually the maths at the time didn't predict that. It would say that most of the energy should be at these very short wavelengths. In fact, it should be all up at there, and this was known as the ultraviolet catastrophe. Something's gone wrong. It doesn't work the way we think it ought to. But at any rate, leaving that aside, it just shows also that here, the yellow is what the sun actually pushes out, or the top of the atmosphere. This is what actually gets through to us on the ground. The atmosphere absorbs a certain amount of the radiation, but you can see that most of what the sun pushes out, most of it is pretty well transmitted to the ground. And I'll just mention the famous greenhouse effect then, which you hear all about global warming. Well, what actually is all that about? Really, what it's to do with is that the sun gives out radiation at these short wavelengths in our visible band and a certain amount in infrared, whereas the Earth, being much, much cooler, gives out radiation at much longer wavelengths down here in that's 10 millionths of a meter as opposed to less than 1 millionth of a meter. And in this region, the atmosphere is more absorptive, and the famous carbon dioxide is a vigorous absorber of radiation in this sort of region. And so the more carbon dioxide there is in the atmosphere, the more it inhibits the Earth radiating its heat away. It doesn't stop the sun's heat getting to Earth because that's at a higher frequency, at a shorter wavelength, where carbon dioxide absorbance isn't so critical. But where the Earth is emitting these sort of things, you can see that round about here, sorry, that's meant to be the transmittance. So right up here means that pretty well all the radiation is getting through the atmosphere. This means that most of it's absorbed in the atmosphere. And you can see, therefore, that in this region here, a lot of what the Earth's surface gives out is absorbed in the atmosphere. So that's the sort of origin of the so-called greenhouse effect, the difference in atmospheric transmission in the region where the sun's energy is coming in, which is up here, and the region where the Earth's energy is going out, which is down there. And if we play around with the amounts of gases in the atmosphere, we play around with how much gets absorbed. And the more that gets absorbed, the hotter the atmosphere gets. And so great global warming. Another little bit, just to conclude, you may have heard about all this 5G stuff and, you know, why you have lots of transmitters. Well, this is because the transmission of microwaves up until this 10 millimeters, which I think is about 30 gigahertz, is pretty good. So there's not much absorbance in the atmosphere for frequencies up to there. So mobile phones, which are all less than 30 gigahertz, and radios and all the rest of it all work pretty well. But as soon as you start pushing up beyond that, you start getting atmospheric absorption problems. And the trouble is, if you want something that's going to have ridiculously large amounts of data going down it so that hundreds of people can have their high definition television transmitted to their phones at once, you need very, very, very high frequency carrier waves to carry all that information, which pushes you up. I gather that 5G, they're talking about 40 gigahertz, which is sort of getting into here. 60 gigahertz, which I suspect on this scale is probably in this bit, is in there, because that happens to be where the absorption isn't too bad. But you see, you're getting, it's even so, it's not as good as up there. So you're going to have your transmitters closer together, because the passage of the radiation through the atmosphere isn't now as good as it was in the lower frequency regime. So that's the sort of issue that are facing the 5G designers, that it doesn't go as far as you'd, I don't know what's happened to this thing, as with the previous ones. So you need to compensate by having the transmitters closer together. So that is the end of the physics, but the little sort of rumination, I feel, is the whole mathematics business, because Maxwell didn't actually intend, he wasn't thinking about light when he was developing his equations. It was all about trying to explain electricity and magnetism, and the whole light business, and hence radio waves, popped out because of the maths. And there have been several in more recent times, even more striking examples of maths sort of leading us into places that we'd no idea of. And this led a very well-known mathematical physicist to actually write a little article entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." And that's a little quote from it at the end, saying that the miracle of it is a wonderful gift which we neither understand nor deserve. I'll let you read the rest of it. So that is quite mysterious as to almost why funny little mathematics, which after all is a human invention, isn't it? It's just us playing around with numbers and lines and geometry and all this sort of stuff. It's a bit trite to say that the world is mathematical, but clearly we are on enough of the right track with this mathematical framework that's gradually been built up across the whole planet, really, by individual people working on different bits, making sure that it's internally consistent with the existing body of mathematics, like building an enormous structure, but it's sufficiently solid and rigid and self-consistent that it obviously is it does reflect some genuine order in the universe, because it's surprisingly right. And it predicts things that we, our little brains, didn't guess until maths said, look at this. It's a wave of electromagnetism. Oh, so it is. And an intriguing phenomenon, really. So that is the end of that. But we'll come on to some bits. This is, I felt, the point at which really science almost thought they'd got everything ticked. Okay, we know that gases are little atoms knocking around. We know that all substances on Earth are made out of a small number of elements joined together in different combinations. We know that light is a wave of electricity and magnetism. It's all looking pretty solid. There are a few little problems, like the ultraviolet catastrophe and one or two other things that are. So, of course, people realize, well, it isn't quite right, is it? Because the maths isn't working. So there's something wrong here. And, of course, it turned out there indeed was. And in actual fact, things completely fell over in the 1900s when we realized that actually the universe wasn't anything like as simple as we thought. In fact, it's very weird indeed. And that's what we shall get on to next time. Right, there we are. Sorry, end of recording I want to try and do. Where's the button gone? Stop recording. Right, there we are. That's, yes, I do want to